Hi, everybody. Happy Friday. So let's resume where we left off last time on this algorithm analysis topic. So very quickly, um, last time we started talking about the experimental approach in terms of analyzing algorithms. So the idea is that like we would implement a certain algorithm by writing the code. Then we would run this code, its actual code, after compiling it and everything, and take measurements and gather data points, many of them. That would allow us to draw essentially like a plot to plot those data points and extract a certain equation. And thanks to this equation, we'd finally be able to make predictions and be able to characterize this certain algorithm and kind of know how it would behave on other inputs for which we don't have certain measures. That was the idea of the experimental approach. And we saw that it had quite a few shortcomings. First, because we have to implement the algorithm that we want to characterize. Then the measurements, they depend on a lot of factors that may like interfere with the quality of the results and so on. It's a pretty complex technique. So let's see another approach which we can describe as a more mathematical approach. So let's see what the idea is. The idea behind the mathematical approach is that we would look at all of the operations that a certain program performs, and we would try to associate a certain cost. So for example, that could be a cost in terms of the number of nanoseconds that one operation takes. So by operation, we mean, for example, like adding two integers to one another, or multiplying them, or dividing them, or adding floating point numbers, dividing floating point numbers, declaring variables, assigning values to variables, comparing variables to one another, accessing an array, and so on. So every single operation that the program can make, we would associate a certain cost to it. And so then we could look at an entire program and see how many times we use those different operations. And because we know the cost, we could just add everything to one another and have an overall kind of cost to that program and derive from it the running time. The thing is, like, it might be very complicated to do that because first of all, we need to look at all of the operations of a certain program. The cost is very difficult to determine because it depends a lot on the compiler that you're using, the level of optimizations of the compiler. It depends on the computer itself, the processor that's executing those operations. And some processors are very fast at doing certain things and others are not so fast and so on. So it's actually like such a detailed accounting might be very, very difficult to do. So instead, we're going to simplify that. We're just going to look at a certain program. We're going to look at the code, and we're simply going to count the statements. We're not really going to look at which operation each statement is, whether it's like dividing floating point numbers or just like simply assigning a value to a variable. We're just going to look at the statements themselves. And then we're going to try to count those statements and to take into account the size of the input data. So let's take an example here that'll be easier to understand. So it's kind of the same example as the three-sum, except that the three-sum is actually pretty complicated. We might study it in discussion next week. Here, I decided to go to another example that I called one-sum, which is really simple. It's, imagine you have an array of a certain size, so array A of size n, And essentially you scan this array from beginning to end, and you count the number of items in this array that are equal to 0. So you see, like 3 sums, we're trying to find all of the triplets that would add to 0. Here, 1 sum, we just try to find the number of items that are 0. And so the goal here with this super simple program is to try to count how many times each statement in this program will be executed. And actually, like, you could pause the video very quickly and try to do it yourself and then come back. Okay, let's do it together now. So let's see. So let's look at this statement, for example. This statement, when we initialize count equals 0, that statement will be executed only 1 time, right? And actually, we could even already say this one, the return statement will be executed only 1 time. Now, what about this for loop? This for loop, we see that we have 3 sort of sub-statements. We have the initialization, we have the condition, which will be evaluated at each iteration. We have the increment, and then we have the body of the loop. So let's look at all of those members separately. So let's look at this one. How many times will this sub-statement be executed? Only 1 time. Like, the initialization of the loop will be executed 1 time. What about this one? This one will be executed as many times as we iterate through the loop. This loop will go from 0 to n-1. So this statement will be executed n times. Now, let's look at the body of the loop. So this statement, the if statement, will also be executed n times, because it will be executed from I equals 0 to I equals n-1. The count plus plus now, this one depends actually on the input data. If the array does not contain any item that is equal to 0, so the if condition always fails, then count plus plus would never be executed. It would be executed 0 times. Now, on the other hand, if the array A contains only items that are 0, then every time the if condition will kick in, and this count plus plus will be executed n times. So it really depends on the input data. And finally, I left it for the end. This condition, there's a little trick here. You have to remember that in a for loop, the condition, the stop condition, is evaluated even before running the loop for the first time. So this stop condition will be evaluated n+1 time, like once before we get into the loop, and then n times throughout the n iterations. So that's pretty much the idea, and I summarized it on this slide as well. So now that we have the frequency of every single statement, what does it give us? Well, it gives us the entire running time. And here I made the calculation for the worst case scenario, which is when the array is full of zeros. And so we go through this statement, count plus plus, all the time. If we add up all of those frequencies, which are all dependent on the input size n, that's the estimated runtime that we have at the end for n plus 4. So let's take a more complex example now. Let's look at another example called 2sum. So two sum, again, it's an extension of one sum and it looks exactly like three sum. The idea is that we would try to find pairs of values or of items in an array which sum is 0. And it's really like the same kind of algorithm as three sum, but less complex. So let's do it again. Like we could count all of the statements. So this one we said will be executed one time. This one will be executed one time. That will be executed also one time. That will be executed n plus one time. That will be executed n times. So here it's pretty easy. However, the inner loop is a little bit more complicated here. So how can we think about it easily? Well, let's study it a little bit more. When I will be equal to 0, then j here will start from I plus 1. So j will go from 1 up to n minus 1. And that's when the inner loop stops. So 1, 2, n minus 1. Then we'll go back to the first loop. I will be incremented by 1 and we'll do it again. So the next time I will be 1 and j will go from this time 2 to n minus 1. Next iteration, I will be 2 and j will go from 3 to n minus 1, and so on. And so eventually, I will be equal to n minus 1 at the very last iteration, and j will not even enter its own loop because j will be equal to n, and that will fail the stop condition and we're not even gonna like execute anything. So that's what we have. And so here, if we count, it means that the j loop will be executed here n minus 1 time, n minus 2 times, n minus 3 times, and here down to 0 times. So how many times total does that make? Well, here, it's typically what we call a sum of series, for which the mathematician called Gauss solved. And so Gauss said that like if you have a series that goes from m down to 1, then overall the sum of all of those terms is equal to that. So we could essentially run the same. Like if we want to try to add n minus 1 plus n minus 2 plus n minus 3 and so on down to 0 total, it means that it's half of n minus 1, n minus 1 plus 1. I'm really just like applying this formula, right? With m being n minus 1. And so overall, that equals to n minus 1 times n. And that's essentially the frequency of operation for this term. So actually no, for this term, this term will be executed n time exactly like this one, because we only execute the assignment of j once per iteration of the loop I. However, the j++ and this if condition, those will be executed that many times. And once again, the stop condition for the J loop is the same as here, but plus one time, because it's also executed before we even get into the loop. So this one would be executed also like from n, n-1, n-2, n-3, and so on. So the formula would be a little different. And so overall, if we count everything, that's what we get. And so you see here that like that's exactly this formula corresponds to what I've been showing you here. And for the stop condition of the J loop here, the formula is slightly different. Okay. Once again, if we sum all of this and we take the worst case scenario where in fact, like all of the pairs all sum to 0. So we enter, like we execute every single line all the time. That's the kind of running time that we have. 2 times n to the power of 2 plus 2n plus 4. Now you have to agree with me that it was a little complicated to compute, right? Like we have to apply this like sum of series. We really have to make some huge mental effort to be able to count all of the statements and derive the equation that like gives us the overall running time. Maybe we don't need to count everything like that, and we can simplify even more. Because when you look at it, like that really doesn't help like telling us the running time. That doesn't really help getting us the running time, and that would probably be able to be simplified a lot more. So let's see how we can do that. So first of all, we can try to identify which operation in the entire like block of code in the entire algorithm really represents the best the overall running time. And here it turns out that like what represents the best the running time is this if statement, because that's really like the core of this algorithm is to try to evaluate pairs of items and see if they add to 0. And we saw that the frequency for this statement was this, like half of n times n minus 1. And so if we like expand this expression, we have half of n squared minus half of n. Now let's simplify a lot more. Because we see that like we essentially have two terms. We have the term in n squared and then the term in just n. It turns out that like maybe we could completely ignore the lower term and only like focus on the n squared. The n squared term here, half of an n squared, is called the leading term. And the reason for us to like kind of allow ourselves to only focus on that term and discard the lower terms is very simple. Is that like once you get to a set to an end, sorry, like the input size that starts growing towards large numbers or like even towards infinity, then this lower order term completely disappears, like it's not relevant anymore. And that you can plot very easily. Let me show you here. So here I plotted the two curves, one that's only essentially like half an n squared, and this one is half an n squared minus the lower term, half of n. And you see that like as soon as we get to large numbers, which are not even that large, like 2000, the two curves are completely indistinguishable. Like you cannot tell which one is which. And that's mainly because like this term, the x squared, totally overpowers this small term. Like this one is super small compared to this one who completely like takes over. That kind of notation is called the tilde notation. So it's a way of like approximating a certain curve by only keeping the leading term, because it turns out that like when the input size starts growing, the lower terms, they don't really matter anymore. That tilde notation is definitely a good approximation for people doing algorithm analysis. For us, it's still a little too precise. Most of the time for us, we're going to talk about something else. We're going to talk about something called order of growth. So for example, like if you have a function that's pretty complicated that contains multiple terms, if you simplify it in terms of tilde approximation, it means that you discard all of the lower terms and you only keep the leading term, but you also keep the coefficient. Now, when you talk about the order of growth, you only focus on the growth of the function, and you don't care about the coefficient. So, for example, here with the tilde approximation, you had 1/6 n squared. The order of growth is just n squared. You're just trying to capture like how the curve actually evolves. Like here, half of n squared, oh, sorry, like n cubed, n cubed. And so here, half of n squared, you just keep n squared. Here, log of n, that's just log of n. And in case of like constant time, 3, you just keep the idea that it's constant, so just 1. So overall, like in terms of mathematical approach to characterize algorithms, we do have mathematical tools that allow for a very, very accurate modeling. And some people who are very invested in studying that, that's what they use. People who work in, people who study the theory of algorithm, usually they are fine using approximate models, using a tilde notation. Often that's enough. And for everybody else, including us, we often only just talk about order of growth, which is a perfectly fine way of like determining what kind of algorithm we have and how it compares to other algorithms and so on. So actually, like to give you kind of a notion of what does it mean, the order of growth, when we apply it to code. Let me show you a few examples here. So if we have an algorithm that's essentially just a sequence of simple statements, and it does not depend at all on the size of the input. So if we have an input that we're considering that is, I don't know, of size 10,000 versus an input size of like 100,000, but the algorithm doesn't really like take that size into account, and it's just a succession of m successive statements, then it's just constant. Now we have logarithmic. That would mean that you have a collection of n items, and you go through those n items with like a few iterations. And at every iteration, the number of items that you are considering is divided by 2 up until you reach the conclusion, like you reach the end. So it's essentially like you divide your collection in half at every single step. So if you had an input size of 8 elements, for example, then you would need 3 steps to process those 8 elements. If you had an input size of 16 elements, then you would need 4 steps to go through all of those elements. That means that your algorithm is logarithmic. The binary search that we talked about last time, that's a logarithmic algorithm, because if you have a set of n numbers that are sorted, and in order to find one, you jump to the middle and you discard half of what remains, and you keep doing that, then you will find the number that you're looking for in logarithmic time, like running time. Next, we have linear. So this one is the easiest. It means if you have a collection of n items, then you go through all of them. And it typically, like, it means that somewhere you have a for loop that goes from 0 to n. That's linear. So if your collection n has 8 elements, you're going to have 8 iterations. If you have 16 elements, you're going to have 16 iterations, and so on. Next, we have an interesting one that we're going to talk about later this quarter. It's called linear arithmetic. It's essentially n log n. It's used, for example, in the sorting algorithm called merge sort. And it's also very popular in all of the techniques that are called divide and conquer. So often what's going to happen is that you have a certain collection of n elements. You're going to divide them into repetitively. And that's where the log n part comes in. And once you've divided everything into recursively, you kind of like re-merge everything back together. And this re-merging, like regrouping part is often linear. And so that's why overall you have n times log n. Next, we have quadratic, n squared. So that's typically when you have a certain collection and you apply 2 for loops in a row. So here, typically, like if you had a collection of 8 elements, and so you have an outer loop that goes from 0 to 7 and an inner loop that goes from 0 to 7, total, you're going to make 64 iterations. So 8 times 8. And then we go on, we have cubic, so n to the power of 3. So essentially through 3 nested for loops. And last but not least, we have exponential or factorial algorithms. Those are pretty bad algorithms. It's essentially algorithms where you have a certain number of items and you try the combinations of all of them. So for example, like there's a typical problem called the traveling salesman's problem, where you have a salesman and this person has a list of cities to visit to sell their stuff. And they try to find the shortest route to visit all of the cities and go back to their origin city. That's a very, very difficult problem to resolve. And essentially, in order to find the answer, you would need to try the combination of visiting all of the cities in all of the possible orders. And once you've done that, then you know which order is the best order. But in order to find it, you have to try all of the possible orders. And that's typically a case where you could have an exponential algorithm because you need to try all of the combinations. So to give you even more perspective in terms of what those different growth means, like let me show you a graph where you can see how those algorithms kind of like behave graphically. And that's what you see. Oh, let me remove those marks. Okay. So here you see that we have obviously like constant is great because it doesn't depend on the input size. Then logarithmic is one of the best type of algorithm because it's super fast. It doesn't increase very much, even if the input size increases. Then linear is not too bad, as well as linear arithmetic. Like often when we find linear arithmetic algorithms for certain kinds of problems, like people are fairly happy. Because it's still like kind of, it gives us decent running times. And then we have the category of quadratic, cubic, exponential, and factorial. And those are usually like considered pretty bad or not very well optimized algorithms, because as soon as the input size grows, they start getting really, really bad performances. And finally, to even give you a better example of what it truly means, let's run a quick example. Let's assume that we have a computer with a processor that runs at 1 gigahertz, so fairly fast. And let's assume that this processor can execute one instruction per cycle. And let's assume that we are running an algorithm on an input size n of 100,000. And 100,000 as an input size, it's not that big. 100,000 is the equivalent of the population of Richmond, California, for example. So imagine like you are working for the city of Richmond, California, and the mayor asks you like, hey, we need to run a certain algorithm to, like, I don't know, figure something out about the inhabitants. And so you know that you're gonna have to run some sort of like processing loop on 100,000 items. Or if you do some machine learning, you want to model the brain of a lobster, which also has about 100,000 neurons. And we can agree probably that the brain of a lobster is not that big. So that's your input size. And then it's funny to see, like, according to the kind of algorithm that you're able to come up with, like, are you able to design an algorithm that will run in logarithmic complexity or in exponential complexity? How long is it going to take to process an input size of 100,000 on this 1 gigahertz processor? And here it's staggering to see the difference. So for example, you see that like everything that's from logarithmic to everything that's from logarithmic to linear arithmetic, it's pretty good, right? You're like still way less than a second. So you will be able to process all of the items in just a fraction of a second. If your algorithm is quadratic, so meaning like you have two for loops nested into one another to process all of those items, that's now already going to take 10 seconds. If you have three for loops that are nested into one another, it's going to take 11 days. And now, if the algorithm that you're running somehow is trying to determine all of the possible combinations for this input size, then we're talking about I don't even know how much that is, but I'm not even sure we'll still be alive in that many years. So you see here how important it is to find algorithms that have a good running time complexity, because otherwise on the same input size, you can have a range from a fraction of a second to eternity, essentially. Okay, that's it for today. And we'll continue on for the next lecture. Bye.